Well, let's discuss another circuit. There are three input signals in the circuit, U1, U2, and U3. They are connected to the op-amp's non-inverting input terminal through a resistor respectively. It's still a circuit with negative feedback, so we consider it operating in the linear region. We can analyze it based on the ideal op-amp's two properties, virtual short and virtual open. According to the two properties, we can get that U minus equals U plus equals 0, and I minus equals I plus equals 0 too. Since I minus equals 0, the sum of I1, I2, and I3 equals IF. If we apply KCL to op-amp's non-inverting input, we express these currents in terms of the input and output voltage. It should be U1 over R1 plus U2 over R2 plus U3 over R3 and equals minus UO over RF. Pay attention to the reference direction of IF. Then UO equals minus RF times the sum of U1 over R1 and U2 over R2 and U3 over R3. So the circuit's output is a linear addition of U1, U2, and U3. If all the resistance are the same, which means R1, R2, and R3 are same, then the coefficient of U1, U2, and U3 are same. So it's a perfect addition. We call it ANDer. The minus sign means it's a reverse addition of three signals. Let's say the input and the output voltage waveforms of an ANDer consist of the ideal op-amp by experiment. This is the ANDer, which consists of an op-amp. It has two input signals. One signal is the AC voltage, and another is the DC voltage. The value of the DC input can be adjusted by the variable resistor. The proportions of the two inputs are both minus 1. The output is the inverting addition of the two inputs. Let's look at the waveforms. The yellow curve represents the AC input, and the green curve represents output. The input DC voltage is 0 now. Let's increase the DC voltage. You can see that the output waveform is moving down. It's truly realized the inverting addition of the two inputs. Continuously increase the DC voltage, then the output waveform begins to be distorted, which means now the op-amp is operating in the nonlinear region and doesn't meet the requirement of an adder anymore. We can observe the similar phenomenon by adjusting AC voltage. We can realize the addition on basis of the common operation by op-amp. Next is the subtraction. The subtractor is based on the inverting amplifier and the non-inverting amplifier studied previously. This is the inverting amplifier. UO equals minus RF over R1 times UI. And this is a non-inverting amplifier. UO equals 1 plus R1 over R2 times UI. If op-amp's inverting input and non-inverting input are both connected with the voltage sources, intuitively, UO should be the addition of the two outputs. In other words, UO equals 1 plus R1 over R2 times UI minus RF over R1 times U2. In which U1 represents the voltage source connecting to the non-inverting input, and U2 represents the voltage source connecting to the inverting input. It's a subtractor with different coefficient of U1 and U2. Let's check whether the combined circuit can get the above results and analyze the circuit. It's also a negative feedback circuit with the ideal op-amp, so we can analyze it based on the two properties, virtual short and virtual open. Virtual open circuit means I plus equals I minus equals 0. U plus equals U minus. According to the relationship between the voltage and the current of this branch, I minus equals 0 means the current flowing through RF equals the 1 through R1. The equation is the current through RF, which is UO minus U minus over RF, equals the current through R1, which is U minus minus U1 over R1. Then we can get this result. According to the virtual short property, U minus equals U plus equals U2. Replacing U minus with U2, we can get the same result as the one on the previous slide. It means that the above result got by intuition is right. Obviously, the subtractor is a little imperfect, since the coefficients of U1 and U2 are different. Can we change them to the same? Let's review the whole analysis. In the analysis, this equation cannot be changed, because the topology of the branch is unchangeable. U minus equals U plus is unchangeable too. U plus equals U2 here. If U plus equals RF over R1 plus RF times U2 instead of U2, then replacing U minus, which equals U plus in the equation, the coefficient of U2 will be the same as that of U1. It's obviously right. Now maybe you can understand why I want U plus equal RF over R1 plus RF times U2 just before. We want to make the coefficient of U2 to be the same as that of U1. Now the question is how to improve the circuit to realize that U plus equals RF over R1 plus RF times U2. In this circuit, I plus equals 0 means U plus equals U2. If we want U plus to be such a coefficient times U2 now, you can see the coefficient is just the expression of the resistor voltage divider. So if we add a resistor RF here, does U plus equal RF over R1 plus RF times U2 now? It's obviously right, since I plus is 0 now. Let's redraw the circuit, and we get the improved subtractor. With regard to this circuit, we derive the relationship between the input and output again. We still use the basis of the ideal op-amp's properties, virtual short and virtual open. According to the virtual short property, U minus equals U plus, which is a proportion of U2, equals RF over R1 plus RF times U2. Furthermore, according to the virtual open property, the current flowing through R1 equals that through RF. The current flowing through R1, which is U1 minus U minus over R1, equals that through RF, which is U minus minus UO over RF. Solve these two equations simultaneously, then we can get UO equals RF over R1 times U2 minus U1. It's a very perfect subtractor. The coefficients of U1 and U2 are totally same. Now the analysis of the subtractor is completed. Reviewing the inverting amplifier, the non-inverting amplifier, the adder, and the subtractor, we can find that the analysis on all these circuits is by applying KCL on the non-inverting and the inverting input terminals, and is based on two properties, virtual short and virtual open, of ideal op-amp. Now I have a question for you. Can we apply KCL on ideal op-amp's output terminal? Technically, it's okay. Any node in the circuit should satisfy KCL. But there is a problem if we apply KCL on the ideal op-amp's output terminal. None of the ideal op-amp's two properties, virtual short and virtual open, can tell us the output current of the ideal op-amp. Since the output current is unknown, we cannot get the relationship of the currents through other branches by KCL on this point. So generally, we don't apply KCL on ideal op-amp's output terminal. Another note, in fact, has been mentioned above. The ideal op-amp's inverting input terminal, non-inverting input terminal, and output terminal cannot be considered as a generalized node to apply KCL. Since its ground and power source terminals are omitted, we cannot apply KCL to the generalized node.